Hi, so let's get started with this unit 3. This is the work, energy, and power unit. So in this video, topic 3.1, we're going to talk about something called translational kinetic energy. And that word translational is going to become important because we have to distinguish between that and rotational kinetic energy. So the first thing, an object's translational kinetic energy is given by the equation K equals 1/2 mv squared. So we didn't really define what kinetic energy is, but remember kinetic is motion, so that makes kinetic energy the energy of motion. Something you've probably been talking about since elementary school and junior high. The units, so one thing to note is that all energy, not just translational kinetic energy, is a scalar unit, so we don't care about the direction. And it's going to be measured in joules, named after James Prescott Joule, who did some research on converting mechanical energy into heat. And down here to the bottom right, this is the James Prescott Joule experiment where he dropped the mass there on the right-hand side, causing a cylinder to turn, and thus he was recording temperature or changes in temperature in that little area where you see the paddle device. Okay. Now, something to note is that kinetic energy specifically will always be positive. Okay. And if you look at the factors for kinetic energy, you have two. You have velocity, right? But the thing is, that's going to be squared. So that number can never be negative. And then as much as we know, as of right now, the other factor, mass, can't be negative. Right? So that's why we know that kinetic energy will always have a positive value for those two reasons. One, velocity is squared, and two, again, as we know right now, mass can't be negative. All right? Now, what's going to happen is different observers are going to measure different values of the energy because of their frame of reference. Now, frame of reference, we talked way back in Unit 1. Okay, so remember, that's just based on the measured speed from where they are. Okay, and so that's going to be important. And what they like to do here is, we've been talking about these relationship questions. AP likes to do these questions here. Again, mainly looking at the speed. So note that kinetic energy is directly proportional to v squared. Not v, but v squared. So if you triple the velocity, you're going to 9 times the kinetic energy. And it's also directly proportional to mass, right? So if you double the mass, you're going to double the kinetic energy. All right, so let's look at an example problem. So we have a couple of, we have 3 parts here, all looking at the kinetic energy. We have different things that we're looking at. So one, we're going to find the kinetic energy of an athlete. The next thing we're going to figure out is the kinetic energy we're going to find the mass of this this impact crater or the asteroid that hit it. And then we're going to look at the kinetic energy of a neutron in a nuclear reactor. Okay. So we're going to separate this into 3 sections. The first one, very easy, right? We're given the mass of the athlete. We're given the speed that they're running with. So we're just going to do 1/2 mv squared. So 1/2 times 80 times 10 squared. So that's going to be 1/2 of 80 is 40. 10 squared is 10. So 40 times 10 is going to be 400 joules. So that's just a straightforward calculation. Much like the third one, part C. So if we just jump ahead real quick, the only difference between the first one and the third one is that, look at the numbers, right? The one thing to remember is that here the speed's given in kilometers per second. We need to convert that to meters per second, right? And it's not given in the problem, but we need to know the mass of a neutron. That's given on the formula sheet. So the mass of a neutron is 1.67 times 10 to the negative 24th kilograms. Actually, it should be, I think it's 27. Let me get my formula sheet real quick. Yes, it is to the 27th. I should know that. I wanted to do research with these things. So we're going to do 1/2 1.67 times 10 to the negative 27, and then convert that kilometers per second to meters per second. And I'm just going to need to double check my math. Let me grab a calculator. All right, pull my calculator drawer. I just want to double check this number because it looks like it's 24th on my notes. So half times 1.67 exponent negative 27 times 2.2 exponent 3 squared. And we get 4.04 times 10 to the negative, not 21st. No, that is 21st. 21st joules. Okay. Now let's go into the middle part where we're going to find the mass of this asteroid that hit this impact crater. So we're going to do the algebra to find mass. So K is 1/2 mv squared. So we're going to multiply by 2, divide by v squared. So the mass is going to be 2 times kinetic energy divided by v squared. All right, so we got 2 times 4.2 times 10 to the 23 joules divided by 22 times 10 to the negative 3 meters, or sorry, positive 3 meters per second. Okay, put that in our calculators, and we find the mass of this asteroid that struck the Yucatan Peninsula at 1.73 times 10 to the 15th kilograms. So that's actually a fairly large object. I know it's not as large as Earth, but that's a pretty big object. All right, so in the next video, we're gonna talk about this concept of work, and then we're gonna relate it back to kinetic energy.